A thin beam of light cuts across the night sky, silent, invisible, unstoppable. A drone hundreds of meters away suddenly ignites, its frame melting before it spirals into darkness. No missiles, no explosions, no warning, just pure, concentrated energy traveling at the speed of light. This is real footage from 2024. The U.S. Navy's HELIOS laser system, mounted on the destroyer USS Preble, successfully burned an aerial target out of the sky. And it's not alone. Israel has already deployed the world's first operational laser defense network. China claims it has reached breakthrough power levels. The laser arms race has begun. Welcome to the future of warfare, where weapons fire at 186,000 miles per second, defend endlessly, and cost less than a cup of coffee per shot. What this weapon is? Military lasers aren't the colorful beams you see in movies. Most operate in infrared wavelengths, seen visible to the naked eye, and converts electrical power into concentrated photons that can burn through metal, plastic, and composite materials. These systems use multiple kilowatt fiber lasers combined to create beams capable of output ranging from 60 to 300 kilowatts. That's 200,000 times more powerful than a typical laser pointer. The latest generation includes systems like HELIOS, Iron Beam, and Valkyrie, names that sound like superheroes but represent genuine technological breakthroughs. They're designed to engage drones, missiles, rockets, and small boats at ranges up to 10 kilometers. Unlike conventional weapons that fire bullets or missiles, laser weapons engage targets at the speed of light, lock onto a target, fire the beam, and within seconds, the target's structural integrity fails. How military lasers actually work. Here's the science. A laser weapon converts electricity into photons, particles of light. These photons pass through a gain medium that creates a cascade effect, generating billions more photons, all focused into a narrow beam by precision optics. When the beam hits a surface, it generates effects based on photon wavelength, beam power, and target material. The highest power lasers can heat, vaporize, melt, and burn through different materials. The damage mechanism is thermal. The concentrator energy rapidly heats the target surface. Metal begins to soften, composites start decomposing, fuel tanks rupture, control surfaces fail. For metal under aerodynamic load or functioning as a pressure vessel, failure typically occurs from crack initiation and propagation well before complete burn-through. A 300 kilowatt laser could melt through an aluminum-shelled missile in approximately 2.5 seconds and a plastic-shelled target in under 1 second. But there's a critical challenge. Atmospheric conditions, rain, fog, smoke, and dust scatter laser beams, reducing effectiveness. That SY monosystems use adaptive optics technology that analyzes atmospheric distortion in real time and refocuses the beam to compensate. Real combat tests and results. The testing has been extensive and impressive. In fiscal year 2024, the USS Preble fired its HELIOS system to destroy an aerial drone, verifying functionality, performance, and capability. This marked a milestone. The first tactical laser fully integrated into the Navy's Aegis combat system. The Army deployed a 20 kilowatt palletized high-energy laser overseas in November 2022, marking the U.S. military's first publicly acknowledged operational deployment of a working laser weapon for air defense. But the real game changer, Israel. Israel became the first nation to deploy a combat-ready laser air defense system as Rafael Advanced Defense Systems delivered Iron Beam to the Israeli Air Force. Rafael Chairman Yuval Stinitz stated that after 60 years of global attempts to create effective laser weapons, Rafael achieved a breakthrough 5 years ago. In October 2024, Iron Beam reportedly intercepted 40 Hezbollah drones during actual combat operations in the Gaza war. The interception costs approximately $3 per shot. Compare that to missiles costing millions. Senator Angus King noted the stark economics. $10,000 for hostile drones versus $4.3 million for an SM-6 missile, compared to just $12 for a directed energy shot. Which countries have them? The United States leads in variety. The Navy has 8 optical-dazzling interdictor laser dazzlers integrated into Arleigh-Burke-class destroyers, plus a 150-kilowatt laser weapon system demonstrator installed on a San Antonio-class amphibious transport ship. The Army's developing Valkyria 300-kilowatt system designed to protect troops against incoming drones, munitions, and, crucially, cruise missiles. This makes it potentially the first U.S. laser capable of reliable protection against Russian or Chinese cruise missiles. However, initial soldier feedback on the 50-kilowatt Stryker-mounted systems deployed to the Middle East was characterized as not overwhelmingly positive, with challenges in heat dissipation, electronics, wear, and tactical environment durability. Israel's Iron Beam system operates at 100 kilowatts with a 10-kilometer range. The system uses 2 high-energy laser systems to deliver required energy to overcome atmospheric disruptions and destroy targets. Integration with Israel's multi-layered defense, including Iron Dome, David's Sling, and Arrow systems, creates comprehensive protection. The United Kingdom unveiled Dragonfire laser that can precisely hit targets as small as a coin over long ranges. The UK Defence Ministry claims each shot costs around $13, potentially saving tens of millions compared to missile interceptors. China and Russia are developing their own systems, though details remain classified. Can they melt aircraft missiles? Yes, but with important caveats. The power required depends on target material, distance, and atmospheric conditions. To melt a 12-centimeter hole in a cruise missile requires approximately 550 kilojoules of energy. For missiles with pressurized fuel tanks or components under aerodynamic load, structural failure occurs from crack initiation and propagation before completion. The laser doesn't need to completely vaporize a target, just weaken critical areas until physics does the rest. Aircraft present bigger challenges. They're faster, more maneuverable, and require longer engagement times. Current laser systems excel against drones and slower-moving threats, but struggle with high-speed jets. Interestingly, Chinese researchers found that for hypersonic missiles, a power density around 1 kilowatt per square centimeter appears optimal. Higher power can actually be counterproductive as the damaged area decreases. Weather remains the Achilles heel. Fundamental limits include diminished effectiveness in rain, fog, and smoke, which scatter laser beams, and lasers need to remain locked on to targets for several seconds to inflict damage. But technology is advancing. Boeing's tests showed their laser system successfully locked onto and destroyed targets in foggy, rainy, and windy maritime conditions, using reference beams to analyze atmospheric distortion and refocus the weapon beam. Future upgrades. The roadmap is clear. More power, better optics, improved cooling. The Navy is pursuing the high-energy laser counter anti-ship cruise missile project seeking to deliver 300-plus kilowatt laser platforms to defeat crossing anti-ship cruise missiles. Lockheed Martin delivered a 300-kilowatt system to the Army in 2022, with plans to eventually scale to 500 kilowatts. At those power levels, lasers could engage multiple targets rapidly and handle more sophisticated threats. Future systems will likely incorporate artificial intelligence for faster target acquisition, quantum-enhanced optics for better beam quality, and compact fusion or advanced battery technology for sustained power generation. The Pentagon currently spends approximately $1 billion annually on directed energy weapons. Researcher figure that's climbing. Game changer or hype? Here's the honest assessment. Both. Laser weapons are genuinely revolutionary for specific missions. Against drone swarms, small boats, and short-range rockets, they're cost-effective, fast, and deadly. The economics are undeniable, firing unlimited shots at pennies each versus million-dollar missiles. Israel's combat deployment proves the concept works. The U.S. military's operational systems aboard Navy destroyers and Army vehicles demonstrate maturity. But limitations persist. Weather degrades performance, power requirements constrain platforms. Current systems can't replace missiles for long-range, high-speed maintenance in combat zones remains challenging. The truth? Lasers aren't replacing conventional weapons, they're complementing them. They fill a critical gap in layered defense, handling threats too numerous or too cheap for expensive missiles. Within 5 years, expect 300 to 500 kilowatt systems as standard on major warships. Within 10 years, megawatt-class lasers capable of engaging ballistic missiles. Within 20 years, space-based systems protecting satellites and potentially striking ground targets. The laser revolution isn't coming, it's already here. The question isn't whether lasers will transform warfare, but how fast militaries can deploy them before their adversaries do. The weapons of science fiction are now weapons of fact, and they're being pointed at the sky above us right now.